Good afternoon, everyone. Thank you so much for attending this program this afternoon. I'm Christine Reeder, the Adult Services Librarian, and it is now 4 minutes past 5, and so I think I'll go ahead and start, and we'll be letting a lot of people in because we have a lot of attendees that are interested in our program. But before we get started, I want to thank Ken Williford very much for presenting this for us today. Ken's living in Seattle now and comes to us all the way from Seattle, which is the wonderful advantage of Zoom. Today's program will be recorded. Ken received permission from NASA for us to record it, and it will be put on the Pasadena Public Library's YouTube channel. So if you could please mute yourself. None of your pictures or your personal information will appear in the recording. So just please mute yourself because that does allow for optimal Zoom listening. The chat questions will be put into the chat box. If you could do that, please. And at the end of the program, Ken will take all of the chat questions. So I want to tell you a little bit about the library. While our doors are closed, we have lots and lots of opportunities for you to connect with the library. We have lots of programs for your enjoyment and enrichment, and we have numerous services for you. Our digital services are open 24/7 on our library webpage, and our monthly off-the-shelf keeps you informed. And that's how, I'm sure you all know that because that is how you signed up for today. But we have lots of programs for children, teens, adults, and all ages. So thank you for joining. Our library staff is providing chat and reference services and assisting with our new catalog. So if you have any questions, please be sure and call the library staff. Currently, we are offering contactless curbside service. You may go to our new catalog, select the books that you would like, and make a reservation to pick them up at the site, the branch site that you would like to of Pasadena Public Library. So I want to tell you a little bit about today's program on the NASA Mars 2020 mission and the search for extraterrestrial life. Get set to track this momentous event and be part of the world that will be watching. Program today, as I said, is presented by Ken Williford, the Deputy Project Scientist for NASA Mars 2020 mission and the Director of the JPL Astrobiogeochemistry, the ABC laboratory, which has focused on developing analytical techniques to search for signs of life and environment in some of the oldest rocks on Earth. In the ABC lab at JPL, Williford studies the biogeochemistry of ancient Earth rocks in part to understand how we can apply similar techniques to the search for evidence of life on other planets. And rocks returned to Earth from the surface of Mars, for example. Mars 2020, scheduled to land on February 18th, 2021, is the first planetary mission since Viking with an explicit objective to seek signs of life. The Perseverance will land on the Jezero crater on February 18th. Unlike Viking, which was concerned with seeking evidence of living or recently dead organisms, Mars 2020 will explore rocks deposited more than 3 billion years ago when Mars was broadly habitable and the earliest records of life on Earth were forming. The Perseverance rover will collect about 30 core samples of rock and soil, seal them in titanium tubes, and cache them on the surface for return to Earth-based laboratories by future missions. This program is in cooperation between NASA and the European Space Agency, ESA. So I think I'm going to turn the program over to Ken Williford, the expert that will be able to present a wonderful program for you and answer all of our questions. Thank you so much, Ken, for presenting for us today.
Okay, great. Well, it's my pleasure, and thanks for that great introduction. You covered a lot of ground, actually, so that's a big help. And thanks to everyone who called in, logged in, as the case may be. And thanks, to the library for this opportunity. It's great to be able to talk with you all, especially from afar. So let's get right into it. What you see here is a photograph taken from a drone flying up above Cape Canaveral on the day of the Mars 2020 launch. So back in July 30th, we had a beautiful, beautiful day, beautiful blue sky, and launched Perseverance off toward Mars, which is, of course, the subject of our mission and the subject of the talk this evening. So this is Mars. Before we get into, well, and as you just heard, our landing is scheduled for February 18th. So we're in this very critical, very exciting time right now, within a month of landing. Typically for a Mars mission landing on the surface, there would be thousands of people gathering at JPL to celebrate that, to monitor it, to observe it, and share in the excitement. This is just another example of how COVID, which I know has affected all of your lives, has touched all of us, including the 2020 mission. So we'll have a very limited team at JPL doing the necessary work to get the spacecraft safe on the surface. But other than that, we'll all be watching, including me, remotely. And so definitely check out the website if you want more information on how to tune in to what should be a really exciting program on February 18th. So before we get into more specifics on Mars 2020, I wanted to give you a little historical context on how we got here. I'm going to, this is going to sort of be a whirlwind tour. I'm going to move fast because I want to tell you a lot, but I also want to finish this up so we have plenty of time for questions. So let's shoot for that. So you just saw on the last slide a beautiful mosaic image of the planet Mars, but what you see here, hopefully you can see this, just one little bright dot. This is what Mars how Mars has occurred to human beings for the vast majority of our history. For almost the entire time that humans or sort of human-like animals have been able to look up at the sky and potentially notice Mars, this is the best we could do. A little pinprick of light. With the invention of the telescope, of course, we could bring ourselves a little bit closer and start to resolve this planet as a visible disk in the sky, start to do astronomy, aided astronomy with the telescope, and start to resolve some detail there. Now it's not just a faintly, potentially a little bit reddish dot in the sky. It has some structure to it. And in fact, this amount of structure enabled some early science to go on, mapping the surface of Mars. These are the very famous map produced by Giovanni Schiaparelli in the late 1880s. And I just wanted to read you this paragraph from Schiaparelli's book, La vita sul pianeta Marte. Translated into English, of course, he writes, "Rather than true channels in a form familiar to us, we must imagine depressions in the soil that are not very deep, extended in a straight direction for thousands of miles over a width of 100, 200 kilometers, and maybe more. I have already pointed out that in the absence of rain on Mars, These channels are probably the main mechanism by which the water, and with it organic life, can spread on the dry surface of the planet. So this is 1893. He's writing this on the basis of those kind of rudimentary sketches done on the last page. But it's just very interesting to me. It's fascinating how close Schiaparelli got in his language to the way we describe the search for ancient life on Mars today. Much the same. A little bit after this, so Percival Lowell famously or infamously began looking at some of the same features that Schiaparelli had been noticing, but interpreting them rather as these straight channels and maybe thinking of them as canals. And in fact, you see here the front page of the New York Times in 1909 announcing there is life on the planet Mars. So they had, already figured it out in 1909. And interpreting these straight features not just as sort of natural channels, but as canals, and not only evidence of life, but evidence of intelligent life and civilization. Of course, that idea didn't last long in the scientific community, and in particular, here you see the first image, I believe, to be sent back from deep space. This is the 1965 Mariner 4 mission, showing the first image of the surface of Mars taken from close to the planet. And notice it does not look like a surface full of cities, but a fairly gray and cratered, fairly desolate landscape. Moving forward by a decade, the Viking mission went to Mars and included both orbital and landed components, as many of you I'm sure are aware. And notice the picture's a little bit larger. These are at the original resolution they were acquired. And so the technology is getting a little bit better over that decade, start to resolve some more detail, including these beautiful clouds floating over the Martian surface. Now we get the first images sent back from the surface of Mars with the Viking lander. So we have fantastic cameras orbiting Mars right now. The best we have in terms of spatial resolution is called the HiRISE imager. We are able to see with that HiRISE imager boulders of roughly the size that would cause a problem for a rover landing on Mars. And it's in part on the basis of those cameras, those images, that we select the landing sites. Viking had to take a much riskier approach and selected the landing site for the lander on the basis of inferior cameras compared to what we have now, much lower spatial resolution, and had to send these landers to the surface, and they were successful with two different landers. Viking, as you heard, was really its core mission was to look for evidence of life. And in this case, the question was, is Mars currently inhabited? So there were a number of biology experiments on board this platform lander. And you see here a trench that the robotic arm dug in the surface. That material was delivered into instruments on board the rover, and some life detection experiments were run. There were really 4 biology experiments. The results from 3 of them were clear negatives, so non-detections of life. The 4th, the so-called labeled release experiment, where the soil was sort of fed some radioactively labeled food or media, and then a mass spectrometer was used to detect whether carbon dioxide gas evolved off of that soil as might be expected from metabolism. So if organisms in the soil were metabolizing or eating those organic molecules that had the radioactive label on them, if that stuff turned into CO2, just like when we eat a sandwich and we exhale CO2, bacteria can do the same thing. If bacteria were doing that and the mass spectrometer picked up labeled CO2, that would be consistent with metabolism happening in the soil. Detections were made of CO2, and so in a sense this was a kind of ambiguous result. It was quickly realized that there are what we would call abiotic processes, or a non-biological, purely chemical processes that could lead to the transformation of organic molecules into CO2. It's oxidation chemistry happening on the surface. And I'll just tell you now, there's I would say, quite a strong scientific consensus, not unanimous, but a strong scientific consensus that Viking did not show any evidence of life on Mars. Fast forward now to 1996. Notice there's a sort of 20-year period where there was not surface science done at Mars, but this very high-profile discovery was made in a meteorite that came from Mars, discovered in the Allen Hills of Antarctica. The rock is called ALH for Allen Hills, 84 for 1984, the year it was found, and 001. It was the first rock found that year, the first meteorite found that year. And in this rock, some scientists observed some features like this, so morphologic features with a microscope, in this case an electron microscope, especially this little sort of wormy shape or sausagey shape you see here in the middle of the image, some morphological features like this, but also some chemical features and mineralogic features that suggested to them there was evidence of fossil life in this meteorite. And this was such a big deal at the time. Bill Clinton famously gave a press conference about this. And you can see that on YouTube, Bill Clinton announcing the possible discovery of life on Mars back in 1996. Again, science has moved on since then. And I would say, again, there's a pretty strong consensus, again, not unanimous, that the features in this meteorite do not indicate fossil life. But an organization called the NASA Astrobiology Institute was launched right on the heels of this discovery. And this sort of was like the image or the observations that launched 1,000 ships, sort of. The funding organization that came into being because of this discovery is what paid for my own graduate school, as an example. So many astrobiologists about my age were trained with the the funds that resulted from the attention that this observation garnered. And right after this discovery began the era of Mars rovers on the surface. So here you see the first one, little Sojourner, which was a technology demonstration on the Pathfinder mission. And this little demonstration of this technology changed, revolutionized, really, I would say, planetary exploration with the Mars rovers. So in 2004, a pair of rovers was sent to Mars, Spirit and Opportunity. You're probably familiar with these, with a mission motivated by astrobiology, but an approach which was often called follow the water. Why is that? Because if we're looking for evidence of life on another planet, of course, life could occur in forms that are very strange, silicon-based life, or other wild things we could imagine. But it makes sense to us to start with life as we know it on Earth. And one of the things that all life on Earth shares, no matter what, is that every organism requires liquid water at some time in its life cycle. So this strategy of follow the water was developed, in part because of that, and in part because some good geologic evidence from orbit, from these cameras on satellites, had been emerging that there had been liquid water, abundant liquid water in Mars's past, and there was a desire to potentially confirm those findings by sending a robotic geologist to the surface. And so that was MER's primary mission, and they were wonderfully successful in doing that, in confirming that Mars once had abundant liquid water, or had liquid water on its surface, detecting some of the first habitable environments, ancient habitable environments, so forth. Now fast forwarding to Curiosity. So this was the next Mars rover after the Mars exploration rover Spirit and Curiosity. This vehicle was quite a bit bigger, quite a bit more complex, and notably required a totally different landing system. So a major advance in technology was required. The previous Mars rovers landed using a big inflatable bag. And so Mars's atmosphere is thick enough that you have to deal with it. You have to deal with the heat that increases as you come into the atmosphere. So you need a heat shield. It's enough to slow down the spacecraft as you're coming towards the surface with a parachute. But unlike Earth, where you can come all the way down on a parachute, that won't work on Mars. And so you need another system. You slow down enough with the parachute, and then you break off the parachute. And in the case of the previous rovers, inflate a big bouncy ball that bounces across the surface, opens up, and the rovers rove out. In the case of the Mars Science Laboratory mission and the Curiosity rover, a new technique was developed called the sky crane. And so after the parachute stage, there's a powered spacecraft coming down on retro rockets with the rover tucked up inside. And coming down on powered flight, you don't want to come all the way down on rockets and contaminate the landing site and kick up an enormous amount of dust and rocks that would come back down on the sensitive instruments of the rover. And so it looks crazy, but the spacecraft hovers above the surface, and then the rover is lowered down, the wheels come loose, and then it gets gently placed down on the surface of Mars. Cables are cut on the top deck of the rover with explosive charges, and this descent stage spacecraft flies away and crashes, and the rover is just sitting there ready to go. So a totally new system. It worked beautifully for Curiosity, and they've had great success with their mission, which was largely about looking for strong evidence of ancient habitable environments. So now moving beyond follow the water, not just was there water there or wasn't there, but now what was the chemistry of that water? How long was it there? Were the energy sources for metabolism, the fuel for life, were those things there in any bodies of water that were discovered? And Curiosity and the team did a great job finding evidence of that sort, and have made many other important discoveries as well. So now it comes to Perseverance and the Mars 2020 mission. We call our rover Perseverance. And it looks very similar to the Curiosity rover, and that's quite intentional. In fact, the built into the fundamental kind of core of the mission strategy was to use as much as possible of the successful designs of the Curiosity rover and build another one. We wanted to make some important changes, though, because the prime motivation for this mission was, again, the search for signs of ancient life, but more broadly, to begin the process of something we call Mars sample return. And this is a concept that dates way back to around the time just after the Apollo missions, when the astronauts were bringing home lots of rocks from the moon, and scientists were making incredible discoveries in those about the moon and the Earth system and the solar system broadly. There was a desire to go to another planet and get samples and bring them back. And this has been in the works for a very long time, but with Mars 2020, that process actually is beginning. And we are the first leg of what would be a Mars sample return campaign. So you can't get it all done in one mission. Our job is to go and select the samples and collect them for return, but future missions, which are currently being architected and designed in partnership between NASA and ESA, the European Space Agency, future missions would be required. Those are not quite formalized yet, but they're sort of on the verge of being pursued in earnest. There's a lot of people working on these, and those missions would go and collect our samples and bring them back. I'll say a little bit more about that later. But that's Perseverance. This is another view of Mars 2020. So when you see the great images coming back from the rover and pictures of the rover, we do have a very incredible, very autonomous robot there on the surface of Mars, but it's a huge team of people like this that it takes to design and build the spacecraft for these missions and to operate them. So I said we launched in end of July. We're now in the cruise phase of the mission, which takes about 7 months. We arrive in less than a month. I described our entry, descent, and landing system. Here's a cartoon of the rover being lowered down from the descent stage, gently placed onto the surface. And then we run our surface mission. These are just some images taken from the Curiosity rover, showing you what it looks like from the rover's eye view of the robotic arm getting out there on the surface and analyzing samples and drilling them. We have 4 principal objectives with Mars 2020. The first is to do geology. So again, we're a robotic geologist. So we get on the surface, use our scientific instruments to look around and understand the processes that led to the formation and the alteration of the rocks that we find around us in our exploration area. So we're asking the question, what was the environment like in which these rocks were deposited? Was it a river? Was it a lake? Was it something deep inside the planet, an igneous environment, molten rock crystallizing into solid rock? Was it a volcanic environment, and so forth? We're asking that question using basic geology skills and capabilities on the rover. As we do that, we move into the second objective, which is where we start to do astrobiology. And the first step is very similar to the MSL approach the Curiosity rover took. We're asking the question, now that we know, or we think we know, what kind of environment formed these rocks, could that environment have supported microbial life? So we're again looking for evidence of extremely ancient life. We're not talking about plants and animals here, or complex multicellular life. We're talking about things like bacteria and archaea on Earth, microorganisms, probably microscopic single-celled organisms. Maybe they would have joined together in communities and made things like what you see in this picture here above the word astrobiology. This rock form is called a stromatolite. This is actually almost 3 billion years old, 2.7 billion years old, from Western Australia. This thing that kind of looks like Mickey Mouse ears. This is a shape with this wrinkly layered internal structure and this branched dome shape. People have thought very hard about this and tried to think of a process that could form rocks like this that doesn't require living organisms. And so far we can't do it. So this, to us, even just a shape like this is quite strong evidence that microbial life was living in this environment. And in this case, it was an ancient lake 2.7 billion years ago on Earth. Okay, so this is the sort of thing we'd be looking for in our exploration area. And as we do that, we move beyond, what some of the previous missions have done, and not only ask, could this environment have supported life, but directly start looking for signs of that ancient life that have been left in the rocks. In this case, it's a shape. We show this image here to indicate that we're actually making some spectroscopic measurements that again, we'll talk a little bit more about later, looking at the chemistry of the rocks we see around us. As we do that, we choose the locations in our exploration environment that we believe give us the best chance of having preserved signs of ancient life, but more broadly, signs of how Mars evolved as a planetary system. So whether or not Mars was ever inhabited, we're very interested in how Mars evolved, particularly early in its history when it was more Earth-like. We want to understand terrestrial planets, rocky planets like our own planet and Mars and Mercury and Venus. We want to understand how those planets evolve more generally. Right now, we only have good samples to look at from one planet, our own. So we want to expand that sample set. So choose samples like that to understand how Mars's climate evolved early in its history, how it went from potentially a much wetter place, a more habitable place, to a dry, barren, inhospitable surface environment that it is today. How did that happen? When did that happen? We're interested in all those questions. And of course, the big question, was Mars ever inhabited? We're also doing a lot of work to prepare for future human exploration. So some of the things we do very directly help prepare us for that. So we have a suite of weather instruments on the rover, and obviously measuring the weather is relevant to human explorers who would have to deal with those modern surface conditions. And then we have a technology demonstration called MOXIE, which is a class of technology called ISRU, or in situ resource utilization. And this is where, for MOXIE specifically, The instrument pumps in carbon dioxide, which is abundant in the Martian atmosphere, and transforms that into oxygen using a chemical process. And there's very little, almost no oxygen in Mars's atmosphere, but the ability to turn CO2 into oxygen would be very useful to human explorers. You can imagine they could breathe the oxygen, but the main use is really as an oxidant for their rocket fuel to get them back off the surface. So it's much easier if you don't have to bring all that, all those components of the rocket fuel with you to Mars, and you can send a device ahead that can make some of that critical material at the surface of Mars. Okay, I mentioned that we're part of Mars sample return, the first leg of Mars sample return. This is a diagram that gives you a little sense of how that will work, but basically Mars 2020 will be roving around our exploration zone, choosing samples, taking contextual scientific data, collecting those samples, sealing them and placing them on the surface. 2 missions would launch simultaneously. The current view is that could happen as early as 2026. The missions would be an orbiter and a lander. The orbiter would get itself into orbit around Mars. The lander would land on the surface near our sample collection that we call a cache. And it might have a small rover that roves out, picks up our samples, brings them back to the lander. On the lander is a rocket launcher. So that little rover puts our samples inside a ball called the orbiting sample, or the Oz, puts that ball into the rocket. The rocket launches off the surface of Mars, puts that little ball, the orbiting sample, in orbit, at which point the orbiter then has to rendezvous, capture that sample, all of our samples, and then fly its way back to Earth, at which point the samples inside an Earth reentry capsule are released from that spacecraft, come through Earth's atmosphere, crash into the desert, and folks go out and retrieve the samples, bring them back to a lab. And the lab is something like, imagine the basement of the CDC, the first lab that they go to where they're analyzed for Earth safety. And this is because Mars sample return and Mars 2020 have to follow very closely guidelines that come from planetary protection. And these are international agreements controlling the extent to which we send Earth life to other planets, but also any sample that might contain extraterrestrial life that comes back to Earth has to be handled very carefully and very safely to avoid any unwanted release of that Martian material into the Earth environment. The risk, the chances of something being terribly harmful to Earth life are incredibly low, but it's such a, the potential consequence is important enough that so much design work is done to make sure that everything is encapsulated, double encapsulated. It comes back and it's sealed very well until it's brought into a very safe environment, opened up, tested for Earth safety, and then it moves into the scientific phase of sample return science. Why would we do this? One reason you might do it is as a test case for sending human astronauts to Mars and getting those incredibly precious samples, if you like, back to Earth safely. I should think we'd want to do that with some rocks before we do that with people, but opinions vary on that. It's primarily described as a scientific enterprise. This is just an example of, so we're looking through a microscope in my lab right now, focusing up and down through a microscope slide that has on it a very thin slice of rock that's thinner than a sheet of paper. The rock itself is 3.5 billion years old, and the brown stuff you see in here is organic matter. You'll just have to trust me on that. But these little shapes, these little spheroids, collections of spheres, larger spheres here, and there are some lens-shaped or spindle-shaped things here. We believe these are fossil microbes from 3.5 billion years ago. And in order to get images like this and further study them, you have to do that careful sample preparation to slice the sample so thin that you can shine light through it and put a very fine polish on it. So far, we can't do that sort of thing with a rover. But that's only the first part. That's the sample preparation. The next step for my own research with a sample like this is to take it to an instrument like this called a secondary ion mass spectrometer. This particular one has a 3-ton magnet. So it very difficult to impossible to imagine currently sending something like a 3-ton magnet into space, much less to Mars, to do these kinds of analyses that are required at this point for us to study the earliest record for life on Earth. So much more so for samples from Mars. If we want to really seriously ask the question, did Mars once host life? We want to make measurements like we do on the oldest Earth rocks. In order to do that, we need to get those rocks back to Earth-based laboratories to do that, because we can't send instruments like this to other planets. We can send some very powerful instruments though, and with each mission, the instruments advance. In the case of Mars 2020, we're taking a very similar approach to what we take on these earliest Earth rocks. That last instrument I showed you makes what we call spatially resolved analyses. And so it shoots a beam, in that case of cesium, into the surface and analyzes the chemical composition of a tiny little target that's the size of one bacterial cell or even smaller. And so similarly on our rover, our payload features 7 instruments, but 2 of them are similar to that giant instrument that you saw, but just tiny miniature versions. And they make what are these spatially resolved analyses. So they use a very fine beam. The instruments are called Pixel and Sherlock. They both have a beam size of about 100 micrometers, so about the diameter of your hair, and they analyze an area about the size of a postage stamp or your thumbnail or so. So imagine rastering, moving, a beam that's the width of your hair over about that area and building up a map. And that's the kind of measurements that we're making with Mars 2020. Pixel is mapping, it's using an X-ray beam to map the elemental composition of a rock target. Sherlock is using a laser beam, an ultraviolet laser beam, to map the molecular composition of a rock target. So the molecules that it's measuring could either be minerals or organic molecules. Organic molecules are obviously important when we think about evidence of ancient life, but we also know there are minerals that tend to be associated with life. So carbonate minerals are a great example. Seashells are made of calcium carbonate. Corals are made of calcium carbonate. Many organisms on Earth either secrete calcium carbonate or cause calcium carbonate to be crystallized in and around their bodies. Microbes do this. In your own body, you have phosphate minerals in your teeth and bones. Those are other classes of minerals that are important for biology. But what we commonly see are these tight, intimate interactions between minerals like this and organic matter. And so that's the sort of thing we're looking for, lifelike chemical compositions. When we have mapping instruments and very nice cameras, we're able to look for those lifelike chemical compositions, especially when they occur in lifelike shapes. What are lifelike shapes? Well, I've told you a few times that microbes, when they're living on top of each other, you think of the edge of a pond or the edge of a lake where you have that green scummy stuff like pond scum. Sometimes that pond scum are really little microscopic single-celled organisms living together in communities and layering on top of one another, exuding some sticky substances that then cause sediment from their environment, mud particles and sand particles, to stick in those layers and eventually fossilize them. And so you get, I don't know if you can see my camera image, but you get a rock like this. So this is a stromatolite. You see it's concentric circles. We're looking at a top-down, what would have originally been a dome, so oriented this way like a dome-shaped microbial mat that's then been sheared off by erosion. And so you see these wrinkly layers, concentric circles. So you're looking at a different view of that here on the screen, 3.5 billion-year-old stromatolite. And we're now mapping the elemental and mineralogic and organic composition of that layered rock with Pixel and Sherlock. So we're seeing lifelike chemical compositions occurring in lifelike shapes that conceivably could have been made by microbial organisms living on top of each other. So that's our approach to looking for signs of ancient life. Where are we going? Going to wrap this up quick to make sure we have time for questions, but basically this is an elevation map of Mars, projection obviously, and a few things I want to point out here. These were our 3 top candidate landing sites. So we spent 5 years choosing the landing site, going from something like 40 potential landing locations, whittling it down to 3, which we took then a recommendation of where we thought we should go as a mission to headquarters, and headquarters made the final decision. But notice 2 of them are located very close to one another, and they're on the western edge of this, what is a very, very large impact crater here. This is called Isidis Planitia. And so this giant impact crater here itself sits on the edge of a giant flat area in the northern hemisphere. We call this Utopia Planitia. And it's possible that this giant flat area is an even much larger impact crater. So that could have only formed, even this one we think is large enough that it could have only formed in the very earliest part of Mars's history, when the planets were still sort of sweeping out their orbital zones around the sun, and there were giant pieces of rock that are almost the size of a planet. We would call them planetesimals. When those things were still floating around, this is the time when Earth's moon formed. So we think something about the size of Mars collided with Earth, and giant explosion happened. Earth sort of came back together. A little bit of Earth, which is now our moon, crystallized and orbits around us as a result of that giant impact. Similarly, features like this could have formed, and this crater. It's possible that this was once a northern ocean. So there are some scientists who believe we have strong evidence for an ocean formerly on Mars in this northern area, but the jury is definitely still out on that. If there was, wonder did it come into here, and were the shores of that ocean around here? We don't know, but there's extremely ancient crust around this area. Now zooming in here, we see that our landing site here is this smaller crater. Now smaller, it's 40 kilometers, so almost 25 miles in diameter. So it's still a pretty big feature, but that just gives you a sense of how large this is. Imagine the impact required to create something like this. On the western edge of Isidis here, you have Jezero crater, and it's situated in some of the oldest crust, the oldest rocks exposed on the surface of Mars. So they're very interesting as recorders of that earliest interval of history. We're tucked here in between Utopia Planitia that we talked about, the possible Northern Ocean, this giant impact event, and then this younger event, but still see very old. GA stands for Giga Anna, or billions of years ago. And so this is a giant volcano called Syrtis Major. It's about 3.5 to 3.8 billion years old. Very interesting later interval of Mars's history, very early interval. And then we have Jezero. Zooming into Jezero, a few features I want to point out for you here. First is the crater rim. So you see this rim that defines the crater there. The crater floor is what we would call the middle of the crater. Now, some of the features that really led us to want to land here. So first of all, the inlet channel. So this is a very ancient river channel. I'm pointing it out with my cursor here, like a river canyon that carves its way through the crater rim. Interestingly, we also see an outlet channel. So there are lots of craters on Mars that have a river channel flowing in, suggesting that they may have filled with water, but comparatively few that have also a river channel flowing out, which clearly indicate that this had to fill up with water and then spill out the other side. So not only do we think it was a lake, but it was an open system lake with water flowing in one side and out the other. Very interesting system for us to explore. And then the real kicker is this delta here, this big fan-shaped feature, which really only forms on Earth where high energy flowing water meets low energy standing water. The high energy water in the river can have a lot of sediment, sand and mud entrained within it because of all its energy and flow. When that high energy water meets a standing body of water, the energy drops and all that sediment drops out as well and forms a big pile of sediment like this called a delta, like the Mississippi Delta. And the delta has lots of little microenvironments in it. So a lot of things we're interested in here. This is where we think the lake would have been. So imagine out here, closer towards the middle of the lake, you could think about the muddy bottom sediments of the lake. It's what we'd expect to find down at the base of the delta. Those fine-grained muddy sediments are great at preserving organic molecules, so we're very interested in those. Up here, it's more like sandstone, so all the sand that was flowing down the river. Now, a sand sample for us represents, in a sense, tens of thousands of individual little samples, which are rocks from up here in what we call the watershed that was drained by this river. So this river was eroding bits of rock out here and bringing them down as little grains of sand that we can study now. With that instrument I showed you, the SIMS, that giant instrument with the 3-ton magnet, it's one of the things it's greatest at is studying things like as small as a grain of sand that we then slice up into tiny little microscopic samples. So there's so much science we can do with these sandy samples as well. And then we get to perhaps the most interesting to me is where the shores of the ancient lake would have been. And one of the greatest things about this, so we know that the rocks deposited here, if we know there was a lake, which we have very strong evidence there was a lake, we know the shore of the lake would have been right here, right inside the crater rim. That's interesting because a lot of living organisms, I talked about the pond scum, you know, these scummy green stuff that you see at the edge of a pond or a lake, right at that edge of the water body is a great place for life. So it has a substrate to grow on. It can get the light and the energy it needs. A lot of nutrients, a lot of chemistry going on at that interface between the water and the land. But very interesting, from our orbital spectrometers, we can see that there are carbonate minerals here. So we talked about how seashells are made of calcium carbonate. In this case, it's magnesium carbonate. That's those stromatolites I showed you, including this one. This is made of calcium magnesium carbonate. So carbonate is fantastic for preserving signs of life. So the shores of a lake are great places for life signatures, biosignatures to form, but especially if there's carbonate minerals around, those minerals can entomb those biosignatures and crystallize them into fossils that we could then come back and find. But even if there wasn't life, carbonate minerals are made of carbon and oxygen, and then an element like calcium or magnesium. So calcium carbonate is calcium, carbon, and oxygen. Where do the carbon and oxygen come from? Ultimately, the interaction of, remember I said the Martian atmosphere is rich in carbon dioxide. That atmosphere interacting with water, dissolving the atmosphere in the water, leads to dissolved carbon dioxide, which then ultimately can form carbonate and crystallize out. So you get this little time capsule of the atmosphere preserved in the rocks, potentially around those rim deposits. So that's where I wanted to leave it, and hopefully we have some time for questions, and I'm happy to stick around after 6, you know, if people have questions and want to linger there as well.
Thank you very much, Ken, for a fabulous program. Everybody is just sending me chat questions. They want to know how they can watch this again, because there's just so much to learn from. And when you see all those people that have helped produce all of this project, we have lots and lots to learn. So thank you very much. This program will be put on the Pasadena Public Library's YouTube. Now we have a big question. Wanted to ask, since the helicopter is limited to 90 seconds, what is fully its objective? Also, can wrap my brain around how you have such precision to plan a trip from Earth and a several-month trajectory, and so perfectly land without crashing into any possible objects.
Right. Yeah, so a couple big questions there. One, I didn't mention anything about the helicopter. I knew somebody would ask about it. So you have a helicopter on board the rover, tucked up underneath. And very early in our mission, so within the first 3 months, we plan to drop that helicopter off on the surface of Mars, move the rover safely away, and then the mission of that little helicopter, which is called Ingenuity, it's really a technology demonstration. So this would be a demonstration, in a sense, analogous to that little first Mars rover I showed you, Sojourner, which was a technology demonstration on the Pathfinder mission. We're demonstrating a new potential technology to explore the surface of Mars. So it could really, change a lot about the way we explore Mars and other planets. But its job is to make 5 flights and show, that we can actually do powered, controlled flight on the surface of another planet and on Mars. And so there are major technological hurdles to that. With the thin Martian atmosphere, it's very hard to fly a helicopter at Mars because of that. But it's been demonstrated at JPL now in a chamber, a very large chamber with Mars simulated conditions, with a tether used to simulate the lower gravity of Mars. But we'll see. We'll try to fly that helicopter early in our mission and see how that works. The other question was, how do you have such precision? I think what was being asked is, in effect, it's amazing that we can send a rocket from Earth and land it on Mars in a very specific place. All I can say is I am also amazed. It's just gobstopping talent, of the engineers who are able to achieve that. It absolutely blows my mind as well. So I'm with you, and I have zero involvement in helping the thing get to where it needs to go. But there are people who are true experts and incredible at what they do, who are in charge of that process. And so we just thank them for doing their job well.
So how can you tell which channels are inlet and outlet?
It's a great question. Yeah, we believe that let me see if I can go back. Nothing about this will be obvious, but it has to do with the overall regional elevation changes and the morphology of the channel. There's we could talk about how to interpret river geology or sedimentary geology for a very long time, but hopefully suffice it to say that there are geologists who look very closely and zoom way into an image like this. You can zoom in so closely that you can see, you could really see if there was a person laying down. So our rover is a 2 meters roughly. It's 2 meters high, so about 6 feet tall. And you can see the rover in these images. So it would be much too small to see in this image, but you can get a very good view of the geology and the rock formations with our high-rise camera and other instruments. And so through the interpretation of all those images, the sedimentology is done and interpreted.
So how many government and private sector organizations are involved in this project end to end? Must be a lot.
Many, yeah. I don't know the number, but quite a few. So it's many people and many organizations are involved in putting this together on both sides of that line, as you said, government and private sector.
So how confident are you with the cable cutters that release the rover? It seems a really risky move, says somebody.
Indeed, but this is so one of the considerations of that risk is to make sure all that's done as early as possible in the mission. And this is one of the things that's leading us to want to deploy the helicopter within the first 3 months, because we really want to make sure that hardware that's on the rover that has those charges that are required to cut the cables and do some of those things is fresh. And Mars is not only a very harsh environment for life as we know it, but also for machines. It's incredibly challenging to keep a machine alive and stable on the surface of Mars. There are a lot of challenges, not the least of which is the giant temperature swings during the day. So it actually gets warm enough for ice to melt. The very low atmospheric pressure means ice generally sublimates and just goes straight to the gas phase, but it does get warm enough. It gets above freezing on the surface, but then it gets extremely, extremely cold in the middle of the night. And so having any kind of, so I'm just highlighting the risks. You asked how confident I am. Those things tend to work, knock on wood, but yeah, a lot of testing is done and verification just to ensure that we can have very high confidence that they're going to work. But a lot has to go right.
So people want to know, how did you get involved in this project, and what is your background? We have a lot of young people in today, and if they want to get into this field, how do they go about doing it?
Yeah, well, that's a great question. So I took a very long and winding road to my current job, but to make it as short as possible, a story, I've always been interested in life. I would say I was one of those dinosaur kids and loved dinosaurs early on. But my education was kind of always around biology and geology. I was turned on to geology very early on. My undergraduate degree is a sort of interdisciplinary thing where I could combine geology and biology, and also studied some sustainable development in college. Then went straight to graduate school, did a master's in geology, but I really love teaching, and so I took some time between master's and PhD to teach. And then I also went to film school actually for a couple of years, and thought for a while I would be a documentary filmmaker. Still would love to do that someday. But then decided to go back to graduate school, and it was during my PhD. Both were at University of Washington. And by the time I went back for my PhD, we had the astrobiology program that I mentioned, and there was a lot of funding at University of Washington to put together a curriculum. It's really unique, I would say, the curriculum at the University of Washington, specifically in astrobiology. And so I'm so lucky to have, been able to go through that program and be a part of that. I studied mass extinctions during my PhD. So actually the extinction before the one that killed the dinosaurs. And I was studying how did the carbon cycle and the sulfur cycle, sort of the microbial cycles of the whole planet, how did those cycles respond to this event that extinguished probably 2/3 or more of all life on planet Earth, as far as we can tell from the fossils. So that's what I studied in my PhD. I did 2 postdocs. One was in Australia, in Perth, Australia, where I developed my capabilities or my skill set in organic geochemistry. That was at Curtin University. And then I moved on to the University of Wisconsin in Madison, which is where that big 3-ton magnet instrument is located. So I worked on that instrument for a couple of years. And it was in doing that I started some collaborations that led me to the job opening at JPL. They were looking for an organic geochemist to work on Mars sample return. And so I came to JPL to set up a lab, worked on the Curiosity rover mission, the MSL mission, for a while. And then was asked to, then actually my introduction to Mars 2020 was as what we call a co-investigator. So as part of the team that proposed an instrument to be on the rover. So before I had my current job, I was just part of a proposal for the Sherlock instrument that was one of some 70-ish proposals, of which 7 were selected to be instruments on board the rover. So I joined the science team that way, and then soon after that was asked to take my current job, deputy project scientist, which is to help lead the science team.
What a fabulous route to get where you are. Just unbelievable. Unbelievable. How very exciting. A lot of young people want to hear exactly how you did it, I'm sure, and how they might go about it. You have children. Are they in that same field or interest in it?
I have a 3.5-year-old daughter, so she hasn't quite made up her mind yet, but I tell her she's got a couple years,
A couple years to
or we have to start, grooming her for Ivy
I'm
League.
sure.
No, not really. No, I'm going to take the same approach my parents took, which was to encourage me to do something I really loved. My dad especially hammered that into my brain, year after year after year, and so yeah, I was very fortunate to have. They just sort of let me explore, and
That's good. There's that saying, if you love what you do, it will not feel like work. So
that's right.
you've definitely found it. And so, well, we've got some more questions if you have some more time.
I do, and just on that, for especially for questions like this, I mean, I love being able to answer questions like this, and particularly for young people. But any question you have, look me up. You can pretty easily find me with Google at JPL, and you can send a question through my JPL website. So I'm happy to answer questions that way as well. If you don't get a chance tonight, or you think of something later.
Well, you were very generous to do this for us and definitely very easy to find. So the library is very appreciative. Thank you very much. So will our understanding of whatever is found on Mars be limited by our own understanding of what possibly could exist in a universe?
Well, that's a very interesting and sort of philosophical
No
question, I would
question,
say.
right?
And I would say the answer is emphatically yes. I mean, but if I'm understanding the question right, it's a beautiful question about philosophy of science, and I think it can be extended to just sort of our um, you know epistemology and the how we have knowledge and how we understand anything. To some extent, our understanding of anything new is to some degree limited by our sense of what's possible, right? And so
Right.
saying, like I said, sometimes we know that's happening. Sometimes we say, well, we know there could be silicon based life, or these other radically different types of life, things we can't even imagine. And so it's not, so we are looking, though, primarily our strategy is to look for life as we know it, because we do only have this one example of life on a planet, and all life on Earth, as far as we can tell, shares some important qualities. And so what are those qualities that all life that we know of share? And let's focus on those, because we know that's possible, right? Yes, we could spend more energy looking for things that might be possible, and certainly I hope there are folks who do that. But yeah, our approach is guided by what we know from Earth. But I think you're right to point out that we ought not be limited, or we ought to be careful to the extent to which we limit ourselves in our discoveries by focusing only on what we can imagine.
So how do we go about tracking the landing on February the 18th? What site should we go to?
Yes, I don't have the actual specific site to give you right now, but I will just give you the advice to Google Mars 2020 landing, and you will certainly find our site. So the Mars 2020 mission site, they'll be announcing it, loud and clear on there. There will be, if you find the NASA site, you'll find it. So especially right around that time, the NASA website, nasa.gov, jpl.nasa.gov. I think it's Mars. Well, I don't know, but I would just suggest that you use Google and find your way to the Mars 2020 official website as best you can, and you'll find the info you need there.
Okay. Well, today's program is going to be the link and the information about going to the Pasadena Library, a YouTube channel, will be sent out to everybody that attended today, so that you'll be able to review all of this too, because there's just so much for each one of us to learn from your presentation. It's absolutely fabulous, Ken. People want to know how long is the day, what type of power might be used. Is there any mission to go to Jupiter or other planets? I suppose we could go on and on with the
Yeah,
question.
well, I can hit those first three very quickly. I think how long is the day? The Martian day, we call it a sol, is very similar to an Earth day. It's a slightly shorter than the Earth day, only very slightly shorter, but it's out of phase. So that means our daytimes are out of phase. So it's a whole long explanation I could give you and could go on and on, but one of the things that means is for us to get the most out of our rover, to use it to in its most efficient way, we want to be on Mars time, which means we wake up when the rover is going to sleep on Mars. So when it's becoming night on Mars, the scientists and engineers wake up, get all the data from that last day, make a plan while the rover is asleep, and send the plan up to the rover right before the rover wakes up. That's the most efficient way to use the time. But to do that, and we will do that for probably the first few months, so we'll be oscillating out of phase with our families, and the rest of the world in our schedules. And people can only keep that up for a few months without going completely, crazy, I'm told. And so we do that for a few months, but then we eventually move into a more normal working hours, but that means we lose a bit of efficiency. And so we have certain days where the data from the last day came down too late in our workday to effectively make use of it. And so we have to do only very low risk things with the rover, like move the turret around. We can't move the arm or, do anything where we could risk breaking it because we don't have the latest knowledge of the robot. So that was that. And then the other two, I remember are there missions to Jupiter? There are, and there have been, and there are more envisioned for the future and beyond. So other, very key targets for the search for life beyond Earth are the ocean worlds or icy worlds, the icy moons of Jupiter and Saturn. And these are places where under a thick ice shell, we believe there's a liquid ocean currently today. To access that ocean, we'd have to get something under that thick ice shell. But in the meantime, landing on the surface of one of these icy moons or ocean worlds is something that a lot of astrobiologists would love to do. And one example is the moon of Jupiter, Europa, and then there's a moon of Saturn called Enceladus. But there are other places where we believe this situation exists. And these, I think, are some of the greatest places, if not the best place, to look for evidence of life that may be alive today. So it is possible that Mars currently hosts life, but we think that if so, those habitats are only confined to the subsurface and maybe even only the deep subsurface where we think liquid water is stable today. And so it could be that Mars was once inhabited and any life forms had to retreat into the subsurface to follow the habitable environments deep. And so to look for evidence of what we would call extant life or things living or recently deceased, we would want to send a deep drill system to the surface of Mars to get a sample from deep below in some of these areas. These are also the same areas that humans would want to get to get the resources from Mars to support humans living on the surface. I'm not talking about human cities and colonists, but just human astronauts, even to set up a semi-permanent presence in the far future, would need access to these resources below the Martian surface. I could go on and on, obviously, but yeah.
Fabulous. Well, your knowledge is absolutely extensive, and the Pasadena Library is very fortunate to have had you come and do this for you. And so remember, everyone, that we're going to send a link for the program, how you can see a recording of it. It'll be put on the YouTube, and we're also going to try to send you the link for the NASA Mars 2020 site. And there'll probably be a watch party on February the 18th, right? And we can.
Oh, there will be. Yeah, there's a big series of events. And so you can definitely encourage you to tune in, and there'll be a great show on NASA TV and other things that you can check out. See interviews of scientists and engineers and people from NASA headquarters and a lot of great stuff to check out.
And we'll see you there too. They'll be interviewing you too, I'm sure.
I'll be there in some form or another, yeah. And I'll certainly be watching. And yeah, so we have a lot of stuff in the media in the days before and after landing. But yeah, it'll be a very exciting day. The landing is around lunchtime, Pasadena time. So it's a great time to watch. And it should be quite a day.
Well, it will be, and everyone is thanking you so much. We had a 10-year-old young man here who was really
Excellent.
inspired. So we might have a future scientist or explorer or something following in your footsteps. So thank you so much, Ken, for taking the time
My
to
pleasure.
for
Yeah,
us. It
absolutely.
was a fantastic program, and everybody's going to be paying attention to February 18th. That's going to be a red letter day. So
Excellent. Yeah.
thank you very much. We'll
Okay.
give you a big round
Yep.
of applause. Thank you. Thank you
Woohoo!
Thanks a
Thank
lot.
so
you.
Yeah.
much.
Thanks for coming.
Great,
Yeah.
great, great. Appreciate it very, very much, Ken. And thank you coming to us all the way from Seattle, which is pretty wonderful
Indeed.
too, with Zoom. Okay, bye-bye.
Okay.
Thank
Well, take
you.
care,
Bye,
everyone.
everybody. Thank you. Thank you
Bye-bye.
so, so much.